Let's see one more problem. A copper ring is held horizontally and a bar magnet is dropped and allowed to fall through the ring with its length along the axis of the ring. The acceleration of the magnet as it falls through the ring is equal to g, less than g, more than g, depends on the length of the magnet. G is the acceleration to gravity. You have a copper ring like this and you have a magnet. Let this be north, this be south, it does not count, whatever it may be, it falls through. The reason for falling is the acceleration due to gravity, I mean the gravity. As it falls through, this is the north pole. North pole is coming towards the ring. Therefore, this becomes north pole, that is an anti-clockwise current flows through it. This is the north pole now. Therefore, there is an upward force, magnetic force on this one. Although it is not equal to mg, it may not be equal to mg. Therefore, there is a slight decrease in the value of acceleration. Therefore, it would not fall with an acceleration that is equal to g, but the acceleration would be less than g because there is an upward magnetic force on the magnet. As it falls through, the magnet comes here, north was downwards, right as it is. The magnet has passed through now. Now, the south pole of the magnet is going away from the coil, it is falling down with an acceleration g, but the south pole of the magnet is going away from the coil. Therefore, when viewed from the bottom, that becomes north pole, that is anti-clockwise current flows through the coil when viewed from north pole, when viewed from the bottom. Therefore, that is the north pole. Now, the coil starts attracting it towards it. Now, earlier it was repelling, now it starts to attract. Even now, the acceleration of gravity is opposed by magnetic force. Therefore, the acceleration would be less than g. That is, as it falls through from the top, the acceleration is less than g. As it passes through, the acceleration is less than g. Therefore, the answer is B, less than g. Let us see the next question. An electron moves along the line AB which lies in the same plane as a circular conducting loop as shown. The direction of the induced current is A, clockwise, B, the current will change direction, C, no induced current, D, clockwise. Here you have a conducting loop like this. An electron is moving like this. Electron is a negatively charged particle. Therefore, an electron flowing is equivalent to a current, but the current is in the direction of conventional current is opposite to the direction of the flow of electrons. Therefore, the current flows like this. Now, this current produces a magnetic field that would point into direction here. As the electron comes by, the magnetic flux here would increase. Therefore, this has a magnetic field pointing towards the coil and the magnetic field is increasing. Therefore, there is an anti-clockwise current flowing in the coil. Up to this point, the magnetic flux would increase. As the electron goes past this one, the current is equivalent to going like this. Therefore, the magnetic field would decrease. Therefore, the current will change direction to a clockwise direction. Therefore, the option must be the current will change direction. The answer is B. If you take a conducting rod and move it in a plane perpendicular to a magnetic field, there is an EMF induced across the ends of the rod. That EMF which is moving perpendicular to a magnetic field is called motional EMF. The motional EMF is given by E is equal to BLV, where B is the magnetic field, L is the length and V is the velocity of the rod. If the rod is not moving perpendicular to its length, but at an angle of theta with respect to its length, then the motional EMF E is given by BLV sin theta. Let us solve some problems on motional EMF. A rod of length 2.5 centimeter and negligible thickness is placed perpendicular to a magnetic field of 40 Gauss. It is moved with a velocity of 6 centimeter per second at an angle of 45 degree with respect to its length as shown. The induced EMF across the ends of the rod in microvolts is 6 microvolt, 6 root 2 microvolt, 3 microvolt or 3 root 2 microvolt. The length of the rod is given, that is 2.5 centimeter. The magnetic field is given, that is 40 Gauss. the velocity of the rod is given that 6 centimeter per second, and the angle theta is given that's 45 degree. I have to find the motional EMF E in microvolt. As the velocity is at an angle of theta with respect to length, motional EMF is given by BLV into sin theta. We may not notice this sin theta sometimes because in usual cases the rod moves like this, the angle is 90 degree. In that case that becomes sin 90 degree, that equal to 1. You may not have noticed it, but the actual formula is BLV sin theta. B is 40 Gauss, 40 is 40 into 10 power minus 4 into L is the length of the rod. Length of the rod is 2.5 centimeter, 2.5 into 10 power minus 2 into velocity of the rod is 6 centimeter per second, that's 6 into 10 power minus 2 into sin theta is sin 45 degree, which is 1 over root 2. That's equal to 40 into 2.5 is 100, 100 into 6 is 600 into 10 power minus 4 minus 2 is minus 6. I reserve 10 power minus 6 because the answer is in microvolt. I express this in 10 power minus 6. What remains is 10 power minus 2 divided by root 2. Here is 10 power 2, here is 10 power minus 2, they get cancelled. Therefore, I get 6 by root 2 into 10 power minus 6, which is equal to 3 root 2 into 10 power minus 6 volts, that's microvolt. The answer is 3 root 2 microvolt, that is the answer is D, 3 root 2 microvolt. Let's see one more problem on motional EMF. The problem is a semicircular ring of radius r is falling with its plane perpendicular to a horizontal magnetic field B. At the position M and Q, the speed of the ring is V. Then the potential difference developed across the ends of the ring is 0, pi r BV Q at higher potential, BV pi r square by 2 M at higher potential. The option D is 2 r BV Q at higher potential. Here, if you have a rod like this, if the rod is moving like this, then this rod can be resolved into two components. The one part of the length is parallel to the velocity, if this is the velocity, this length is parallel to the velocity, and this length is perpendicular to the velocity. This length does not contribute to motional EMF, but this length does. Therefore, in this problem, actually if you take a small piece like this, as the rod is moving like this downwards, this part does not contribute, but this part contributes. Therefore, any part going in the upward direction does not contribute, but this part, this total length contributes. As r is the radius of the rod, the total length of this equivalent rod would be 2r, that is equivalent rod. Shape does not match. This rod, in the case of motional EMF, is equivalent to rod of length 2r. Therefore, the length of rod is 2r, and the velocity of the rod is v, and the magnetic field is B. Therefore, the motional EMF induced E is equal to B into length into velocity, which is equal to B into 2r into V, which is equal to 2r BV. The option D is correct, but we haven't checked the last term here. Next thing is, the rod is like this, the rod is coming downwards, the magnetic field is pointing into the board. If I choose axis like this is the z axis, this is the x axis, this is the y axis, velocity is equal to, velocity is along the negative y direction, therefore velocity vector would be minus v j cap, velocity would be minus v j cap, magnetic field is going into the board, therefore it must be minus b k cap. Therefore, force on the charges, force on the positive charges, suppose there are positive charges here, force on the positive charges inside the rod is equal to, by Lorentz force law, Q into V cross B, which is equal to Q into minus Vj cap cross Bk cap, minus gets cancelled, J cap cross K cap is I cap, therefore I get Q into V into B into I cap. Therefore, the force on the positive charges is along the plus x direction. Therefore, in this rod, positive charges would move in the plus x direction to the right, and negative charges would move in the minus y direction, that is to the left. Therefore, if this is the rod, this would be rich in negative charge, this would have positive charge. Therefore, this would be at higher potential, which is Q. Q would be at higher potential and M would be at lower potential. The answer is D. EMF we have checked 2RBV and we have checked which is at a higher potential. The answer is D. 2RBV with Q at higher potential. If you have a rod or a coil which is being pulled out of a magnetic field, then due to motional EMF, there is an EMF in the circuit and there is a current in the circuit and the wire or the rod gets heated up. That's called Joule heating. Joule heating J is given by B square L square V square divided by R, where B is the magnetic field, L is the length, V is the velocity and R is the resistance. Let's solve one problem on this Joule heating. A rectangular coil of resistance R is pulled out of a uniform magnetic field acting perpendicular to the plane of the coil. If the velocity of the coil is increased by 4%, the percentage change in rate of heating is. Joule heating J is given by B square L square V square divided by R. It's the initial rate of heating. Now, the velocity of the rod is changed from V to V plus 4% of V, which is equal to V plus 0.04 V, which is equal to 1.04 V. That's a new velocity. New velocity is 1.04 V. That's 4% greater than the initial velocity. I have to calculate the new Joule heating. New Joule heating J dash is given by B square L square new velocity whole square. That's 1.04 V whole square divided by R, which is equal to B square L square into V square, because there is V square. But you are left with 1.04 whole square. 1.04 whole square is 1 plus 0.04 whole square. This is of form 1 plus x power n, where x is very small. You can approximate this by 1 plus nx. Therefore, this becomes 1 plus nx. 1 plus 0.04 whole square is 2 into 0.04, that is 1 plus 0.08, that's 1.08 divided by R. That gives you B square L square V square by R, that's J. Therefore, this becomes 1.08 J. Therefore, percentage change in Joule heating is equal to final Joule heating minus initial Joule heating divided by initial Joule heating into 100%, which is equal to J dash is 1.08 J minus J is J divided by J into 100%. J's get cancelled. I am left with 1.08 minus 1, which is 0.08 into 100%, which is equal to 8%. The answer is D, 8%.